Hi, welcome back. This is Calculus 2. Today we are going to talk about trig integrals. So in particular, there's some identities we need to have kind of memorized. So let's take a look at those useful identities. In addition to kind of the Calc 1 things that we presume you know, so like the integral of secant squared is tan, the integral of cosine is sine, those things. You should be familiar with I forget what they call it, they're called like quotient identities. So sine is, you could rewrite as 1 over cosecant. And then cosecant, of course, you could write as 1 over sine. Cosine, you could rewrite as 1 over secant, or vice versa, right? If you had 1 over cosine, you could rewrite that as secant. Of course, secant, but just what I said, 1 over cosine. Of course. Tangent, of course, is 1 over cotan, but we presume you also know it's sine over cosine. And then likewise for cotan, that's 1 over tan, the same as cosine over sine. All that great stuff. The Pythagorean identities, we presume you know. So sine squared, if you don't have these memorized, you have to have them memorized. Do what you can, make some note cards, whatever you gotta do. Tan squared, these will not go away. These aren't the kind of things that, oh, we don't need those ever again. No, these will not go away. So sine squared plus cosine squared is 1. If you divide everything by cosine squared, you get the second identity. If you divide the first identity by sine squared, you get this third identity. There's some books call these I think the half angle formulas. Cosine squared is 1 plus cosine 2 theta over 2. And we do need these, okay? These aren't, just for the sake of whatever. We do need these identities. And then the last identity we'll sometimes use, sine 2 theta is 2 sine theta cosine theta. But that really, in a nutshell, is what you need. And of course, in addition, you need to know the basic trig integrals and trig derivatives. Okay. Okay, so you need that stuff memorized. All right. The progression in the book, they kind of give you forms of integrals of products and quotients of trig functions. So the first kind of form you'll see is products of sines and cosines. You'll have some sine function raised to some power times some cosine function raised to some other power, and they'll ask you to integrate that thing. Okay, so for example, you have the integral of sine the fifth x cosine to the fourth x dx. And the way you handle these is to convert everything inside the integral into either cosines or sines, and then leave one function left over for the u sub, so to speak. Okay, so what? Well, I'm going to look at the first guy because its exponent is odd. And I know I can remove one factor to kind of serve as my leftover bits for the u sub. So I'm going to rewrite sine to the fifth as sine to the fourth x, cosine to the fourth x, and then have this one extra leftover sine dx. Okay. Why? Because now I can convert this thing into terms of cosine, right? And then do a u sub for cosine, and the differential of cosine will be sine x dx. Well, negative sine x dx, but we can deal with that. Okay. So what? Sine to the fourth x is really just sine squared squared. And then I could rewrite sine squared squared as 1 minus cosine squared x squared. And lo and behold, I've changed this integral into an integral in terms of cosines. And then I could just do a u sub. Okay, so it's a common theme in these problems. Convert everything in the terms of one function with one left over for the derivative portion. So again, if you let u just equal your cosine, then the differential will be that end part, kind of, with a negative on it. Right? And then you can zip through the integral and do your substitutions, and it just turns into a polynomial of sorts. Which you should be able to integrate using Calc 1 methods. So you can factor out the negative if you wish. The signs are gone. And then foiling 1 minus 2u squared plus u to the fourth times u to the fourth du. I have to distribute. So this will be minus. You can distribute that minus inside the integral if you wish, but I'll just leave it on the outside. We got u to the fourth minus 2u to the sixth plus u to the eighth du. And then you'll have minus, after integrating, u to the fifth over 5 minus 2u to the seventh over 7 plus u to the ninth over 9 plus c. And then back subbing cosine, distributing the negative. Cosine to the fifth x over 5 plus 2 cosine to the seventh x over 7 minus cosine to the ninth x all over 9, and then plus the integration constant. Okay, so that's kind of your standard operating procedure for that type of problem. Maybe we should look at one of these. So number 4, it doesn't seem like it's the same problem, right? But it's the same idea. So what you're trying to do is convert everything inside the integral into terms of one function, either the sine or the cosine, and then have some leftover bit for your differential. Okay, so there's not much you could do with that sine inside that radical, right? I'm not going to be able to kind of factor one factor of sine out of that because it's really sine to the 1/2. So I see that odd exponent up there. Well, I can, convert this in the cosine to the fourth and have one leftover function cosine for my differential part when I do my u sub, right? And then you can convert the cosine to the fourth into terms of sine just by noting again, well, cosine to the fourth is cosine squared squared. And then I can use the memorized formula. So this formula in particular is the one we're using right now to convert that into 1 minus sine squared. And then do your u sub on sine, right? So what do we got? 1 minus sine squared all over square root of sine. So everything in the integral is kind of in terms of sine with one left over bit for your u sub portion. Okay, so we're going to turn this into an u integral by replacing signs everywhere. So du again is just cosine t dt. So dt will be du over cosine. And of course, then we have the integral of 1 minus u squared squared all over square root of u. We'll just write u to the 1/2 times cosine t, and then you get the cancellation with the differential that you did with the u sub. Okay. So goodbye. Let me mark in my notes that I did this problem. I did this one. I did this one. Okay. Foil out the top of numerator portion, 1 minus 2u squared plus u to the fourth over u to the 1/2 du. And then you could butterfly this guy. So it would be 1 over u to the 1/2 minus 2u squared over u to the 1/2 plus u to the fourth over u to the 1/2 du. And so that will be u to the negative 1/2 minus 2u to the 4/2 minus 3/2 is u to the 4 halves minus 1 half, rather, is 2u to the 3 halves. And then 8 halves minus 1 halves will be 7 halves. And then you can do power rules on those characters, and then back sub. Okay, so this will be u to the negative 1 half plus 1 is positive 1 half, divided by 1 half is the same as multiplying by 2. U to the 3 halves plus 2 halves is 5 halves, divided by 5 halves is the same as multiplying by 2/5. U to the 7 halves plus 1 is 7 halves plus 2 halves, which is 9 halves, divided by 9 halves is the same as multiplying by 2/9. And then finally back sub. We can rewrite this as square root sine t minus 4/5 sine t to the 5 halves plus 2/9 sine t to the 9 halves, and then plus c. And that should do the trick. Okay. If you don't have this extra function floating about, what section I'm on? I guess I'm on section 3. You're going to have to use those half angle formulas that I gave you in the beginning. So if you have something like sine to the nth power or cosine, I don't want to confuse things. So let me just write it down. So, or something like cosine to the nth power. You usually have to use these half angle formulas. And the problems in the software, they'll give you one where they kind of give you a reduction formula, this number 8. But in general, you're not going to have that, offhand. You're not going to have this memorized. You're not going to be able to kind of look it up if you're doing a test or something like that. You won't be able to pull that off. But the kind of, if it's an even power, so in our case it has to be even. And this problem in number 8, it's not really an even power anyways. You wouldn't be able to do this method. But if it is even, you can do the following. So this is problem 2 in the homework. Let me put a star there so I know I did this problem. The integral of sine to the 4th of 5 theta d theta. Okay, so how do I pull this off? Well, I'm going to rewrite it as sine squared squared. Okay. And then I could use these half angle identities up here. Right? So they're used often. In the next section, you'll use them even more. But sine squared is 1 minus cosine 2 theta. And so you always double the angle when you use it, even though we call it half angle formulas. In our work, we double the angle in this direction. So it'll end up being 1 minus cosine, not a 5 theta, but you multiply it by 2. So you get 10 theta, and then all over 2. And then, of course, we have to square it. Sometimes they call those formulas the reduction formulas, because what you're doing is reducing that exponent, so you can go ahead and just integrate like a cosine or a sine. Okay, so anyways, I got to FOIL the numerator, so it'd be 1 minus 2 cosine 10 theta plus cosine squared 10 theta all over 4 d theta. And then I'm going to go ahead and change that into 3 fractions. So I have 1/4 minus 1/2 cosine of 10 theta. So I can do both of those terms using integration. But this last term is still a troublemaker because it has a power on it. So what you have to do is use the reduction formula again on the cosine squared of 10 theta, this portion right here. So what do I have? I have the integral of 1/4 minus 1/2 cosine of 10 theta plus 1/4, and again the reduction formula or the half angle identity will say 1 plus cosine double the angle, so you get 20 theta all over 2 d theta. And then we can go ahead and simplify and combine terms inside the integral. So this would end up being 1/8 plus 1/8 cosine 20 theta, and so now everything inside the integral we can integrate. Let's combine the 1/4 and the 1/8. So that give us 3/8. So you want to simplify and combine like terms before you integrate. Otherwise, you're just giving yourself more work to do at the end. And the more work you have to do, the more probability you have for mistakes, right? So you want to kind of just do as little work, the less work you have, the less probability of error. Okay, so the integral of 3/8 is 3/8 theta minus, you could do a u sub if you want, but it'll end up in a factor, giving you a factor of 1/10. So you'd have 1/20th sine of 10 theta plus, and here on the third integral, you'd have a factor of 1/20th, so that'd be 1/60th sine of 20 theta, and then plus c. Okay. From there, we kind of work with integrals in terms of, rather than sines and cosines, we turn our attention to secants and tans. Okay, so you can see a couple of those problems in the homework. There's a tan one. There's number 5 is one of these. So it's kind of the same idea as the cosines and sines. What you want to do is convert everything inside the integral into terms of either secant or tan, and then have a leftover, some leftover factors for the derivative of your u sub. So you're either going to be doing a u sub for secant or a u sub for tan, excuse me. So your leftover portions, if you do a u sub for secant, you're going to have to have an extra factor of secant and tan laying around. Okay. If you do your u sub for tan, at the end of the day, you're going to have a leftover factor of secant squared to pull this off. Okay. So an example of kind of like the prototypical type, this is example 5 in the book. And again, let me mark down that I did this problem. What do we have? Secant to the 4th 3x times tan to the 3rd 3x dx. It looks like we can kind of pluck off. So if you do tan as your u sub, you're going to need 2 factors of secant. So what we kind of do is pluck 2 factors of secant off, and then we need to make sure that the leftover bits, we have enough factors to turn into tans, right? So you're going to need an even number of factors left over in order to use those identities to turn the secant squared into a tan squared. Okay, so that's kind of how I proceed. I'm going to borrow 2 factors of the secant, and then I'm going to convert the secant squared in the front there into 1 plus tan squared. Why it's these formulas. So if you have sine squared plus cosine squared equals 1, and you divide through everything by cosine, you get tan squared plus 1 equals secant squared. So you could replace secant squares wherever you've seen them with tan squared plus 1. Or I wrote 1 plus tan squared. Okay, so now everything in the front is in terms of tans, and we have this leftover secant squared portion. So I can just go ahead and say, all right, I need my u to be the tan of 3x. So your differential will be that secant squared thing at the end of the integral dx. And you could do a straight replacement there. And then, of course, chain rule, we need a factor of 3. If you want to, or you could solve out like we always do, dx is du over 3 secant squared 3x. So what do we have? The integral of 1 plus u squared times u squared times secant squared 3x times du all over 3 secant squared 3x, and then you get that nice cancellation. You can factor out 1/3, distribute the u squared, so you get u squared plus u to the 4th du, and then you're kind of home free, right? So this would be 1/3 power rule it, u cubed over 3 plus u the 5th over 5 plus c. Back subbing, distributing, you get tan 3x cubed all over 9 plus tan to the 5th of 3x all over 15, and then plus c. Okay. Seems like I made a mistake somewhere. Hold on, let me pause the video. Oh, I see it. I put u squared back here. I totally apologize. It should be u cubed. Then this will be u cubed, u the 5th. This will be u the 4th over 4, u the 6th over 6. Sorry. So this will be u to the 4th over 12. And then this will be u to tan to the 6th over 6. It's 18, right? 3 times 6, 18. Okay, sorry about that. All right, so, problems like number 5 there in the software are just kind of variations on this idea. Let's make number 5 the video quiz du jour. So we have the integral of 7. You can see the answer there, so you can check your answer. Tan x squared all over secant x. And this problem, I mean, I don't want to, this isn't really one where you have to do the, you don't really have to do kind of a u sub on this one, the more I think about it. This one isn't really, but I want to do one that's more similar to the problem I just did. So, they don't really have one that's all that similar. I apologize. Not really. None of them are all that similar. Yeah, so this one is actually a lot easier than the problem. I'll give you the u sub, and then you can get it from there. But the kind of the transformation you want to do is, so it won't be similar. I'm just warning, it's not all that similar to example 5 there. But what you'll do is just rewrite tan squared there using the Pythagorean identity. So that's going to be secant squared minus 1. And then you're just going to butterfly it. So I'm kind of almost doing it for you. But once you butterfly it, you should be able to just integrate using kind of elementary methods. You have to reduce that thing. The 7 secant squared over secant will just be 7 secant, and then you can integrate 7 secant. You probably don't have that one memorized, but it's the ln of secant plus tan. And then 7 over secant is just 7 cosine, and you can integrate that because you have that formula memorized. Yeah, so we'll make that the video quiz, though. You can see the answers sitting there. Hopefully you can get it from here. Okay, let me just note that in my notes. Okay, so I mean, they're going to give you standard procedures, but at the end of the day, you got to use your brain. Okay, there's no way around it. So for problem 5, it doesn't exactly follow the procedure, and number 3 doesn't really follow. I mean, if you let u equal tan, the derivative is just sitting right there. The derivative of tan is secant squared. So it'll be u, the integral of u. There'll be a factor flying around in there, but your u sub would be just tan in that version. You don't have to really convert everything else into terms of tan or something. Let's see. Number 7 we did. This number 7, again, it's really not a matter of kind of any, it's really not, again, in the line of example 5. It is kind of considered one of those problems, but let's just look at it really quick. Tan squared x dx from 0 to pi over 6, right? So you use your, again, these Pythagorean identities, right here, these things, to convert it into something you can integrate right off the bat. Tan squared is the same as secant squared minus 1. And then you could just integrate the two pieces because those are elementary integrals. So the integral of secant is just tan x. The integral of 1 is just x. And then you're left with just evaluating, right? So tan of pi over 6 is 1 over root 3 and minus pi over 6. And then minus tan of 0 is 0 minus 0. So, use your brain at the end of the day. That's kind of where you should be at. Let me see. Oh, so there is one other type of problem, number 6. And I wouldn't expect you to, I wouldn't put one like this on a test because you need to use these product to sum formulas. So maybe I should even give this a whole nother section title. So when you have two functions of sine and cosine, but they have different angles inside of them. So for example, sine of mx times cosine of nx dx, or some variation on that. So you'll have sine mx sine nx, or cosine mx cosine nx. And for these problems, you use the product to sum formulas. And you'll have to look those formulas up usually. I don't even have them memorized. I just rarely ever use them. So for example, one like number 6 there, you have the integral of sine of 3x sine of 2x. Let me mark that I've done this problem in my notes. The formula for the product of sum in the book is that sine mx times sine of nx is equal to 1/2 times cosine of m minus nx minus cosine of m plus nx. Okay, and once you do that transformation, you'll be able to integrate it. So we'll have, you can factor the 1/2 out of the integral, and then you have cosine of 3 minus 2x, which is just x, minus cosine of 3 plus 2, which of course is 5x dx. And then you can integrate each term by term. So the integral of cosine is just sine, and the integral of cosine 5x is sine 5x over 5 plus c. And then you can distribute, and you got your answer. Okay. Maybe I should do, I'll do the reduction formula and then we'll call it quits. So where the heck is it? There it is. Okay, so I would not, you do not memorize this formula. Okay, this is a formula that you'd find in a table. Back before we had calculators to do integrals, we had just books of integral after integral after integral, and there'd be all of these kind of things in those. So you can determine, you can make these formulas up, and it's a lot of fun to do that just using by parts, and you can kind of tell that looks like a by parts formula. But if you have something like sine of n, sine x raised to the nth power, you can simplify it using this formula. Again, you would not do this on a test, but in our case, we have sine to the 5th power x dx. So our n value in this first part is 5. So you'd have negative sine to the 4th x cosine x all over 5 plus 4 all over 5 integral sine of 5 minus 2 is 3x dx. From there, you'll have negative sine to the 4th x cosine x all over 5, and then plus 4/5, and then we're going to use this formula again on the sine cubed part, right? So you'll have, this case, n is equal to 3, So you have negative sine squared x cosine x all over 3 plus 2 all over 3 integral sine of 3 minus 2, which is 1 now, x dx. So now you can integrate that thing, and you'll end up with negative sine to the 4th x cosine x over 5 minus 4 sine squared x cosine x over 15 plus 8/15. Integral of sine is negative cosine, so let's change that to a negative. And there you have it. Okay, so just kind of maybe a math history lesson there, if nothing else. And then you should be good from there. I think, you know, number 10 kind of looks like you have to do one of those, multiply it by the conjugate on top and bottom. So I'll just give you a hint. So what I would first do is multiply top and bottom by 11 minus sine t. I believe that would kind of, would that even, I don't know what the heck I just did. I hit some button and who knows. Anyways, what the heck is that doing? Jeez. I didn't even think you have to go that far. I just completely hit some buttons again. I don't know what I'm doing. All right. I'm looking for the draw button. There we go. All right, so I think for this one, you just do a u sub on the denominator, right? So u is 11 plus sine t, and then du will be the cosine. Okay, so I think that one, there's your hint. Number 11, let's say you just rewrite it off the top of the bat, right? So this would be secant, 1 over secant is the same as cosine, and then 1 over tan is the same as cotan. And then you could rewrite cotan, right? So cosine x times cotan is really just cosine x over sine x. And then you would have the integral of 4 cosine squared x over sine x dx. And then you could do a Pythagorean identity and then butterfly. So you'd end up with integral of 4 all over sine x minus 4 sine x. Sine squared over sine x is just going to be sine x. And then that would be the integral of 4 cosecant x minus 4 sine x. And you're expected to be able to integrate those both on your own. Anyways, let's call it quits there. Hopefully that helps, and I'll see you in the next video.